Okay, everyone. Welcome to this meeting of philosophical issues in space science. And it's a real pleasure to be able to introduce our speaker today, Manasvi Lingam, who is based at the Florida Institute of Technology. So many of us will be familiar with Manasvi's recent book. I should really call it an epic rather than a book because of the scale of the work. Life in the Cosmos, which we've been reading. And he's going to be talking to us today about false positives and priors in the search for technosignatures.
Great. Many thanks for that very generous introduction, Dr. Kavi. It's a pleasure to be here. And I think this enterprise is very fascinating and very needed. I'll comment on it briefly at the end of my talk. But without any further ado, let me get started. So here is the outline of the talk. And sections 2, 3, and 4 are going to be, so to speak, the meat of my discussion. And 1 and 5 will be about some material pertaining to it. So let's get started with some preliminary remarks. Most of the work that I'll be presenting here, in fact, virtually all of it, is going to be work that has been done with the CATS collaboration. And the CATS stands for Characterizing Atmospheric Technosignatures. It's funded by a couple of NASA grants, one of which is listed here. It consists of Adam Frank from the University of Rochester, Jacob Harkness from the Blue Marble Space Institute of Science, Ravi Kopparapu from NASA Goddard Space Flight Center. It includes me, Sophia Sheikh from the SETI Institute and the University of California, Berkeley, and Jason Wright from Penn State. So what are the objectives of my talk? I'll be using quite a few italics, and I apologize for that because I think the words that I've put in italics are ones that I would like to emphasize. So I'll be looking at a brief selective and pared down overview of why priors and false positives are important when it comes to assessing the plausibility of technosignature candidates. And then I'll provide a short summary. There's a typo here. I'll provide a short summary of some of the arguments that have been put forth for and against technosignature searches. And lastly, I'll conclude with summarizing some of the work that our own collaboration has done in the context of atmospheric technosignatures. So clearly, given the amount of time available, the level of detail is going to be not as much as I would like. And that will also mean some corresponding loss of nuance as well. So I would like this talk to focus more on outlining various possibilities and, acknowledging the fact that many of the things that we are discussing today are open-ended and ambiguous. So what's the format? I would like to stick to the format that has been mentioned on your website, which I think is a very nice format. So I hope to finish the talk in about 40 minutes and then allow for 30 to 35 minutes of Q&A and an open-ended discussion. And secondly, from what I understand, this is a collaboration between the philosophy department and astronomy department. I'm going to emphasize the broad details and skip some of the technical aspects. My primary goal is to, pave the way for a deeper discussion and exploration of these topics in the future. And these topics are, of course, highly intricate and, of course, quite contentious as well. So let's get started with a very brief history of this field. So, of course, the plurality of worlds is a concept that goes back to the ancient Greeks and beyond. And if we look, for instance, at the likes of Giordano Bruno in the 16th century, we see some explicit speculations regarding intelligent life as well in his book, Dell'Infinito Universo e Mondi. But then if we go to the 20th century, we see even in the early and mid 20th century, the idea of searching for extraterrestrial intelligence through electromagnetic signals. Here is one such quote from Ernest William Barnes, who was a mathematician and scientist, also the Bishop of Birmingham, among other things. So here's the code. As I have already indicated, I have no doubt that there are many other inhabited worlds and that on some of them, beings exist who are immeasurably beyond our mental level. We would be rash to deny that they can use radiation so penetrating as to convey messages to the Earth. Probably such messages now come when they are first made intelligible, a new era in the history of humanity will begin. So that was Barnes in 1931. Most of the times, however, people prefer to date the modern era, as I call it, of the search for extraterrestrial technological intelligence, SETI, which to the pioneering paper by Cocconi and Morrison, who wrote in 1959 that one could search for targeted narrowband radio signals at a frequency of 1.42 gigahertz. So at a very particular frequency, which corresponds to a wavelength of about 21 centimeters. And this particular proposal was a theoretical one, but the first such study was carried out in 1960 by Frank Drake of the famous Frank Drake equation. And this project was called Project Ozma, named after one of the characters in the Wizard of Oz series by Frank Baum. And Project Ozma focused on the two sun-like stars that are near to the sun, namely Tau Ceti and Epsilon Eridani. In the same period, other potential signatures of technology emerged in this period, apart from radio signal and apart from optical signal. One such famous example is the notion of the Dyson sphere, which was also speculated upon in the science fiction novel Star Maker by Olaf Stapledon in 1937. And then there was also the idea of searching for probes, which was put forth by the British engineer Ronald Bracewell in 1960. And moving on to the 21st century, SETI pioneer Dr. Jill Tarter coined the term technosignatures as an analogy with biosignatures in 2007. And this particular word is very useful because on the one hand, it highlights the correspondence as well as the complementarity of the searches for technological and non-technological life. And on the other hand, it's a broader term that encompasses a wider range of technological signatures. Now, currently, the research that is being conducted in this field still includes the search for narrowband electromagnetic signals of the radio or optical kind, but also several other manifestations of technological activity. Some of the reviews of this subject in recent times include the review by Jason Wright from Acta Astronautica, as well as the book that Dr. Kavi alluded to. One such example of a non-electromagnetic, non-radio technosignatures are atmospheric technosignatures. And these were proposed as early as 1980. But then they've really seen more of a resurgence in the past few years. And then I'll be returning to them later in the talk. That completes the first part. Now let me head on to the main parts of the talk. So first, I would like to talk about a simplified Bayesian framework. And this Bayesian framework essentially parallels the methodology that was presented in the review paper in astrobiology by Catling et al. Now, I focused on a deliberately pared down approach. One could make it a lot more complex by taking instead of having binary hypothesis, you could allow for a continuum of possibilities, and then the probabilities that we discuss would be converted to probability distribution functions and so on. So there's three things we'll be focusing on. There'll be the data, there'll be the hypothesis, and then there'll be the context. So D refers to the detected signal or data, namely the potential technosignature candidate of interest. T refers to the hypothesis that there are technosignatures that are arising from extraterrestrial technology and or extraterrestrial technological intelligence. C refers to contextual information. And by contextual information, what I mean is that all kinds of data that are not directly derived from or related to the signal. So for instance, if you're looking at an atmospheric technosignature, namely some kind of a gas that could be produced by technological activity, um, any kind of supporting information would be contextual information. For instance, if we were to know something about the planet's habitability, such as knowing whether it has a magnetic field or not, or if we were to know something about the planet's biosignatures, such as detecting both oxygen and methane in the atmosphere concomitantly, now that would be one more example of supporting information. And this kind of contextual information can also help clarify and pinpoint the nature of D, which is the potential technosignature, namely the signal that we are focusing on. Now, what is our goal? Our goal is to find P of T given D, C. So what we mean is that we want to find a probability of the hypothesis, namely that there's technosignatures coming from some kind of extraterrestrial technological activity. Now we want to find the probability of that hypothesis being true, given the data and given the contextual information. And the starting point is Bayes' theorem, or rather the extended Bayes' theorem, and which is shown here in equation 1. I won't be focusing too much on it. It's fairly standard mathematical derivation, and the details can be found in different sources. And this by starting from this expression, one can simplify it through a series of mathematical steps which involve the use of Bayes' theorem further, as well as the definition of conditional probability. And finally, the final expression we end up with is given by equation 2. Now, equation 2, as you will see, has two variables in it, one of which is P of T given C, and the other is this variable xi. So let's just examine what they are. So P of T given C essentially embodies the prior likelihood of T, of this hypothesis T, given the contextual information available to us. So there is some contextual information that is still available. So it's not just P of T alone, but P of T in light of whatever supporting information we have. And then this ratio xi is defined over here. And it is essentially the ratio of the probabilities that the data we observe are generated from extraterrestrial technology versus not being generated in that manner. So the other ways by which the same signal could be generated could include biological but non-technological activity, non-biological processes, or even terrestrial processes on Earth. For example, radio signals that might be that might actually be arising from near the Earth, but be misinterpreted. So this ratio xi essentially serves as a measure of the false positives for technosignatures. So if xi is high, then we can say with high, then it would mean that the data is much more compatible with coming from extraterrestrial technology than it is from other sources. So we see, as I mentioned before, that these are the two variables alone of interest. So what we can do is we can plot this function, namely the probability we are interested in, which I've highlighted. We can plot that as a function of the two variables. And that is shown right here in this color plot. Ideally, if we want to be fairly confident about the hypothesis being true, given the data and the context, we would want P of T given B and C to be as high as possible. So we would want the red shaded region would be the ones of interest to us. And so when do we move into this red shaded region? And conversely, when is P of T given D, C on the low side? Let's look at these further. First, we see, if we look at this figure, that quite a large portion of the figure consists of a region where P of T given D, C is very low. So so if we want this to be high, what we would ideally require is that the product of these two terms should be much greater than unity. And this can be verified from the figure as well as by inspecting the final equation presented a few slides before. So if we In order for this product to be high, we actually require two conditions to hold at the same time. First, we require Xi to be much greater than 1. And what does that mean? So that in turn means that there must be a minimal chance of the data actually arising from some kind of non-extraterrestrial technological sources. By that, I mean there should be a minimal chance of some kind of false positives arising. So we would essentially want to, it would be advantageous to have candidates that are intrinsically much more likely to be produced by extraterrestrial technology than they are by other sources. For instance, if you were to find narrowband electromagnetic signals, prime number signals, coming from tens of light years away that are extremely narrowband, and then there's a certain sequence, there's some kind of a structure to them. Well, that would pretty much constitute strong evidence for some kind of technological activity being involved. So clearly, Xi being much greater than 1 is one important part. But then the other thing is that it's not just that Xi has to be much greater than 1. The prior P of t given C must also be sufficiently large in order for this condition to hold true. So it's not just Xi. So it's not just that we want signatures that are very unambiguous, but you also need a relatively high prior. And in particular, the product of these two must be sufficiently larger than unity. And in the opposite scenario, when we either have signatures which are ambiguous, or when we have a very low prior, then we end up with the outcome of P of T given D comma C being much smaller than 1. So the posterior probability would become very low, and this would, in a sense, be undesirable. So the way I've structured this talk is, rather than trying to focus a lot on results, I would like to, at each stage of my talk, to highlight some of the open and open-ended questions that come into being. So we see that one of the key variables that matters is this prior P of t given C. And so this particular factor, what kind of values we assign to it, is going to be regulated by the amount of contextual information available as well. For instance, if we have a planet and we are looking at an technosignature from that planet, and if we know through other information that it seems to have signs of life, it seems to be in the habitable zone, it seems to be habitable, etc. That's not, that is one situation. And then there might be another situation where the technosignature candidate is coming from a planet which seems a priori hostile to life. So one of the first questions is, how can we assign values to P of t given C based on the data available? And secondly, what do we do about P of t itself? And remember, P of t refers to the probability of the hypothesis being the prior probability of the hypothesis being true, but in the absence of any contextual information. And this is, of course, something that has been debated a great deal, because P of t would be roughly the same as saying that we are looking at the probability of the likelihood of extraterrestrial technological intelligence arising. And there's a long history of thought which has argued that this is many orders of magnitude smaller than unity. I've summarized some of the classic references here, which come from evolutionary biologists like George Gaylord Simpson and Meyer, etc. And then there's been more recent studies, such as the one by Snyder-Beatty. And if it were to turn out that P of t given C is much smaller than 1, which in a sense is loosely compatible with some of these publications, but only in a loose sense, then we would see that the posterior probability, which is the one we are interested in, which ideally should be as high as possible, would become much lower than unity. For instance, consider the scenario where log of p, where the prior probability is 10 to the power minus 5. We see that in that case, regardless of how high regardless of how low the false positives are, you still end up with somewhat low probabilities. So this becomes, a broader question that one needs to think about. Namely, on the one hand, there are certainly some camps which have argued that the likelihood of uh, technological intelligence is extremely low, and then there's others who would maintain that this is a very plausible and likely outcome. And so there's this path that we have to navigate between the scilla of having P of t given C going to 0, and then the caret disk of P of t given C going to 1. And this is, of course, a matter that has been debated quite extensively. And, I would like to refer to Dr. Kavi's papers in last year and also this year. I think the second one just came out a few days back in the Philosophical Quarterly. And then moving on with the open-ended question, P of t given C, which again, as I said, has connections with the likelihood of technological intelligence emerging, shares some connections with the composite factor FLFIFC from the Drake equation, which I'll be returning to in more detail. Of course, one crucial thing to note is that the Drake equation embodies mean values for all of its variables, whereas what we are discussing here, because of the nature of the contextual information, it means that we must look at it on a case-by-case basis. So, in a nutshell, how do we solve a problem like this posterior probability? And so that's the first part. This part essentially has lays out two things. First, it emphasizes the importance of accurately quantifying false positives, which are embedded in the form of the variable xi. And it also talks about the importance of trying to accurately estimate the prior P of t given C. And both of these are, of course, open-ended questions. And in a sense, what I'll be discussing in the next two parts of my talk will focus on these two aspects, one after the other. So let me get to the case for and against technosignatures. So instead of discussing P of t given C henceforth, I'm going to concentrate on the broader concept of P of t. And well, although I won't be discussing P of t directly, remember that P of t, in a sense, involves the likelihood of the emergence of technological intelligence. So what I would like to focus on is a slightly different question, which is how many worlds in the Milky Way may host technosignatures, which we call NTech, and how many of them may host biosignatures and bio. And so basically both of these, when I say technosignatures or biosignatures, it refers to those that are detectable. So for instance, you might have life on a given world, but it might be in a subsurface ocean, and it may not produce any tangible biosignature, in which case it would not be included herein. So this, of course, is again a topic that has been studied a great deal. And I would like to refer to this publication from the CATS collaboration, which came out, I believe, 2 weeks ago or so. I've provided the link below in case people would like to look it up. And what we are going to do here is that we are going to compare NTech with NBio. So there's a typo here that should be NTech. So we all, I think many of the audience would be familiar with the famous or infamous Drake equation, which is given by equation 3. So R star is the rate of star formation. Fp embodies the fraction of stars with planets, and P embodies the fraction of the number of habitable planets per star. FL essentially refers to the fraction of those worlds that go on to actually produce life. Fi refers to the fraction of life-bearing worlds that go on to produce intelligence. Fc refers to the fraction of worlds with intelligent life that go on to develop communication. And L is the longevity of such species. So what we can do is we can construct similar equations for estimating the prevalence of worlds with detectable biosignatures and technosignatures. And what we do in the case of biosignatures is to work with equation 4. And in this case, however, we interpret FL somewhat differently. Namely, FL is interpreted as the fraction of planets that actually go on to develop biospheres which produce detectable biosignatures, and LB refers to the average length of time that such biospheres remain detectable. And then for technosignatures, we can do a very similar thing, except that we have this extra factor Ft, which essentially embodies the fraction of those life-bearing worlds which go on to produce detectable technosignatures. And in a sense, it resembles FIFC in the canonical Drake equation. And lastly, LT is the analog of LB, and it is the average length of time over which technosignatures would be detectable. So if we take the ratio of these two terms, we end up with this fairly simple looking expression because a lot of factors cancel out. So it is the product Ft times the ratio of the two lifetimes over which the signatures, the respective signatures are detectable, whether it be technological signatures or non-technological but biological signatures. So what's the canonical case against technosignatures? First, many have argued that Ft is much smaller than 1. And the reason being that, again, I won't be getting into it because obviously a lot of ink has been spilt on this particular matter. And, there have been arguments that resort to evolutionary contingency and which make the case that technological intelligence is very far removed from being some kind of a near inevitable outcome. And then moving on to LT and then LB, if we were to look at the Earth as an example and look at humanity as an example of a technological species, well, people have used that to argue that LT by LB is much smaller than 1. So, for instance, we know that life on Earth has been detectable for at least a couple of billion years since the Great Oxygenation Event, which happened about 2.4 billion years ago. And then moving on to technosignatures, it depends on when we think technology on Earth would have been detectable, but it's very unlikely that it would have been detectable before the Neolithic Revolution, which happened about on the order of 10,000 years ago, more precisely around 12,000 years ago. So there's a typo here as well. This should be LT. And so what we see is that if Ft is much smaller than 1, and the ratio of these two timescales is much smaller than 1 as well, then it stands to reason that N-tech by N-bio would be much smaller than 1, and it could be many orders of magnitude smaller than unity. So that's the canonical case. Now, if we look at what we call the maximal case for technosignatures, now this is admittedly only in the most optimistic scenario, as I've highlighted over here. And in that particular scenario, what we see is that Ft could actually be boosted to quite a substantial degree, again, depending on whether any of these technological species were to seed other worlds with technosignatures as well. So this could happen if any of the technological species in question could develop interstellar travel and therefore lead to the spreading of technosignatures. And the other thing we do is we summarize many of the arguments that have been put forth to, and this is really more of a historical summary, but indicate that maybe we shouldn't really be looking at the Earth and humanity alone as guides to the longevity term LT. So in principle, it could become quite large in the particular case, in the admittedly optimistic case, where technology were to outlive its creators. And so far, I've just talked about the numbers game in a sense of comparing N-tech with N-bio, but then there's also other matters such as ambiguity, which ties in with false positive, as well as detectability. So you want a signal to be strong and detectable. And what I'll be presenting soon is in the form of chlorofluorocarbons, is that we might be getting to the case where the atmospheric technosignatures become of comparable detectability as that of atmospheric biosignatures. So again, the second part and the open-ended question. So I said that you could have FT, which is the fraction of life-bearing worlds that go on to produce technosignatures, could be amplified through the activities of technological species, such as interstellar travel, and then could be other things such as terraforming, directed panspermia, etc. Now, of course, FT cannot be amplified ad infinitum because at some point we run into the tension with the Fermi paradox, which relates to the apparent absence of extraterrestrials on or near Earth. So, what are the avenues by which we resolve this tension? That's one of them. And then, secondly, with regards to the longevity term, which is in the case of ETI, this would be LT. And what are the approaches that we could take? So, in the case of humanities, the very well-known doomsday argument, has been debated very extensively, and as to whether it would constitute a good guide for estimating the longevity of our species. So, this brings up the broader question of how we deal with LT in particular. And thirdly, if we just go back to the ratio of N-tech to N-bio, which is essentially, remember the ratio of the number of worlds with detectable technosignatures to that of detectable biosignatures, I talked a bit about FT and LT. Now, if LB is generally taken to be large, and this is why we think LT by LB could be smaller than 1, but there's really not been much study of what LB would look like. And remember, LB is a mean value. So on Earth, it's true that it is, a few billion years. But what is the mean value of LB now? That's still something, that needs further unpacking. And there have been some studies here and there which have suggested that LB could be dominated more by a large number of worlds which have very transient biospheres. So that's part 2 of my talk. And then the part 3, and in a sense, this relates to the whole prior discussion because it looks at N-tech versus N-bio, and then also, presents some of the arguments why N-tech might be much smaller than N-bio, in which case we would assign a low prior. And then on the other hand, there could be an optimistic scenario where N-tech is not that much smaller than N-bio and could even be larger under optimistic circumstances. Now, moving on to looking at some different technosignatures, I'll also use that to talk a little bit about false positives as well. And this is work that has come out of the CATS collaboration in the last couple of years from 2021 and 2022. So the first, and I'm going to focus exclusively on atmospheric technosignatures, which, as the name indicates, are technosignatures that are manifested in the form of gases in the atmosphere. So the first is nitrogen dioxide. On Earth, biogenic sources, and when I say we use the word biogenic or biological in this talk, for the most part, I'm referring to biological but non-technological aspects. So in this case, biogenic sources refers to biological but non-anthropogenic sources. And the amount of nitrogen oxide, which is represented by NOx, that are produced by biogenic sources is around 5.6 into 10 to the power 9 kilograms per year. Lightning, which is an abiotic or non-biological source, generates 5 into 10 to the power 9 kilograms per year. And anthropogenic sources, which are the ones, essentially relating to technological activity, produce 32 into 10 to the power 9 kilograms per year. And if we focus on nitrogen dioxide in particular, which is the formula NO2 as shown here, the primary anthropogenic source for nitrogen dioxide comes from combustion. So given that the anthropogenic sources are more prevalent than the non-anthropogenic sources, it was explored as a potential technosignature candidate by Paparapu et al. For an Earth-like planet orbiting a Sun-like star as well as a K6 star, which is essentially a star with roughly 70% the mass of the Sun, at a distance of 10 parsecs, using a proposed future telescope known as a LUVAR-like telescope with an aperture that is at a diameter of about 15 meters. And it turns out that nitrogen dioxide has prominent spectral features in the region of 0.2 to 0.7 microns, which is shown right here. So if you look at the panel on the right, the ones in blue correspond to the signatures coming from nitrogen dioxide. And we see that there's a plethora of other species present at wavelengths more than 1 micron. But in the wavelengths of 0.2 to 0.7 microns, it shows up quite prominently. So Paparapu et al. Looked at how many hours of observation time would be needed to get to a desired signal to noise ratio. And in astronomy, a good benchmark is taken to be a signal to noise ratio of 5. And to get there, you would need about 600 hours of observation time. And then the second atmospheric technosignature I want to mention are the notorious chlorofluorocarbons. So these have been used historically in various applications in industry. The best known, of course, is that they were used as refrigerants before their use was banned under the Montreal Protocol. And they've also been used in other contexts, such as in manufacturing packing materials as well as aerosol sprays. Moreover, these gases are quite long-lived and are very efficient greenhouse gases. Now, one interesting thing about CFC11 and CFC12, which are two particular types of chlorofluorocarbon, is that both abiotic as well as biological sources are unknown, at least on Earth. So the detectability of these CFCs was first analyzed for habitable planets around white dwarfs in a paper of Lynn Gonzalez and Loeb in 2014. And subsequently, this was generalized to study planets around regular stars, because white dwarfs are known to harbor planets, but we haven't really found any in the habitable zone so far. Well, now the detectability of the same molecule was assessed for this very well-known planet called TRAPPIST-1e, which is one of the planets in the habitable zone of the star TRAPPIST-1, which is about close to 40 light years away from Earth. And this particular detectability was assessed using a telescope which is already functional, namely the JWST. And this was done by a group in 2022, so it's Huck Misra et al. And what is shown here is the transmission spectrum, so the kind of spectrum that would be generated if you were to observe light that has passed through the atmosphere of TRAPPIST-1. And we see that there's many different cases shown. The one in green corresponds to the scenario where there's no CFCs present whatsoever. And this would correspond to the spectrum, sans any technological activity. And then the blue would correspond to the curves, which are commensurate with that of Earth today, whereas some of the other curves correspond to higher levels of CFCs, which did exist in the 1990s. So the highest concentration of CFCs was nearly twice of what we have today. And what we see on the right is the panels for TRAPPIST-1e, and on the left, it is shown for a hypothetical planet orbiting a star of temperature 3300 Kelvin. I would like to focus more on the left panel. And what we see here, again, looking at the left panel, is the amount of observation time that would be needed to get to a given signal to noise ratio. And what we see, and this is done for the JWST, so what we see is that even if we assume a concentration of CFCs akin to what we see on Earth today, if you want to get to a signal to noise ratio of about 3, you would essentially need, which is not optimal, but it's not bad either, is that you would need something on the order of hundreds of hours, a few hundreds of hours of observation time. And then there's also a similar calculation shown for the other hypothetical planet that I mentioned. Now, I want to emphasize that TRAPPIST-1e is not a hypothetical planet. It was found in 2017 and has been quite extensively studied. So what are some of the questions associated with this? What we see from the examples of NO2 and CFCs is there's quite a contrast. So in the case of NO2, the non-anthropogenic sources of NO2 are, are quite substantially smaller than that of the anthropogenic sources, but they're not completely negligible. In fact, they're about a factor of 6 or 7 times lower. Whereas in the case of CFCs, we see that there's really no viable pathways for producing these molecules in the absence of technological activity. So this, of course, brings up the question of, let's say that we have a given technosignature candidate. How do we assign the likelihood of false positives to that particular candidate? For instance, in the case of NO2, we see that there are plausible pathways that could generate a non-trivial amount of NO2, whereas in the case of CFCs, it's not quite so clear. And then, of course, this leads into broader questions, such as, is the Earth it's a good proxy for carrying out these kinds of assessment? And if we were to, and if it's not, then we would, of course, have to resort to some kind of theoretical modeling to envision what kind of other pathways could give rise to putative technosignature candidates. And in the case of atmospheric technosignatures, this would mean that we would have to account for unknown sources and sinks of atmospheric gases. Now, this is, of course, a problem for both atmospheric biosignatures as well as technosignatures, namely, how do we deal with the unknown? And for instance, due to the uh, reported detection of phosphine in the atmosphere of Venus, which of course has been contested since, if we were to grant that there was phosphine in the atmosphere of Venus, then again, many of the known pathways on Earth are not very effective at producing phosphine. So then that brings up the question of what other pathways could do the job. And then looking ahead, I just want to touch on a few broader things. First, of course, the main point that I wanted to convey was that there's a lot of fundamental questions and ambiguities about how we address these issues of priors and false positives in astrobiology. So if we have some kind of a signal, how do we deal with the plausibility of that signal actually coming from a biological source, whether it be technological or non-technological? And so this, of course, this first point pertains as much to technosignatures as it does to biosignatures, albeit with some differences. So in order to truly understand and grapple with how to deal with priors as well as false positives in this domain, it requires a lot of concerted and directed thinking. And there's many promising opportunities that I see for synergy between philosophy and science, and in this case, astrobiology. And there have been some very nice writings that have tried to indicate the two-way conversations that could happen. So there's a work by Carlo Rovelli from 2018, as well as the publication of Laplan et al. From 2019 in PNAS. And in a broader sense, how do we approach and anticipate the unexpected in astrobiology? This, of course, is something that Durham University has been thinking about in the form of Peter Wicker's paper in 2020 in International Journal of Astrobiology, as well as Chris Covey's 2022 paper. And in a broader sense, of course, there's also the monograph by Stanford that explores similar themes in the form of unconceived alternatives. And proceeding in this broader vein, there's also another thing that that needs to be grappled with, which is the nomological vacuum, as it's called, which was, of course, put forth in the context of evolutionary biology by John Beatty in 1995 and expanded on further by others, such as Russell Powell in 2020. And this same nomological vacuum confronts us in astrobiology as well. And then, so, lastly, I would like to conclude with this quote from Heraclitus of Ephesus, which seems quite apposite to me. If you do not expect the unexpected, you will not find it, for it is hard to be sought out and difficult. So that concludes my talk. I think I went a little over time, but yeah, still enough time for questions, and I'd be happy to take them. Thank you for your attention.
Thank you very much, Manasvi. That was fantastic. I really enjoyed that.